Okay, so here we're going to be looking at just a summary of all these rules for finding derivatives that allow us to get the derivative of a function without having to use the limit as h goes to 0 of that difference quotient. So rather than finding the derivative using the limit process, we'll have some shortcuts we can take. So the constant rule just says if you're doing the derivative of some constant, you're going to wind up getting 0. So think about why that is. If your function were some constant, then the derivative of that would equal 0 because derivative is slope. And a constant like that, if you have the function being a constant, that's just like y equal 5, so that's just a horizontal line, and it would have a slope of 0. Now this notation d dx is just another way of indicating that you're finding a derivative of something. And the d dx is emphasizing that you're doing the derivative of c with respect to the x. And c is just some constant. Okay. All right, now the simple power rule, that's going to be the most important thing in section 3.2. Right? And what it tells you can do is that you can take, the way this is going to work is the exponent will come down in front, and then you'll have x, and then it'll be raised to the n minus 1 power. You'll have to subtract 1 from your exponent. Okay? And so this is when you're doing the derivative with respect to x, and then you have just an x raised to the nth power. Okay? That's the simple power rule. Okay, there's going to be a one that has an extra little piece to it when you're doing the general power rule, when the function maybe is not as easy as just x. Okay, but anyway, if you have, for an example, if you have a function like x to the 4th power, then what this is saying, to get the derivative, you bring the 4 down, and then you subtract 1 from the exponent, and that's going to be the derivative of the function. Okay. Now the constant multiple rule is good to know. All right, so what it tells you is that you can just wind up bringing the constant along. When you're doing the derivative of some number times u, where u is some kind of differentiable function. So u might be something like x squared. Okay, then you can just carry that constant along, okay, and then just do the derivative of u. Okay. Now the sum or difference rule is telling you if you had to do the derivative and you had two functions that were being added or subtracted, that it is okay to do the derivative of each function. And so the derivative with respect of u we would do, and then we'd come in and take the derivative of v. Just do those two things separately. So really, these three right here are going to be what allows us to quickly find the derivative of a polynomial, because polynomials are just sums and differences of a bunch of terms that look like that 4x to the 3rd. Okay. All right, now those 4 there at the top, those 4 right there, you do those in section 3.2. So we'll look at this in section 3.2. Now, in section 3.3, we're going to be doing the product rule and the chain rule. Okay, those are very important, and they do not work like limits work. And they're also written sometimes in a variety of ways. And I highly recommend that you think of it like this. Okay, so when you're doing the derivative of a product, you cannot just do the derivative of each factor. You can't do, it is not just the derivative of u times the derivative of v. Okay, that's not correct. Don't do that. Okay, let me write it like this. So it's not that. Okay, what it really is the derivative of one function and that's not to the first power, that's a derivative symbol, okay, times the other function as is plus the derivative of the other function times the first function as is. Now, because addition and multiplication are commutative, you will see this rule written in a variety of ways that are all equivalent to that, okay? But I highly recommend that you think of it this way, and the reason I want you to do that is so that you are sure to do the derivative of the first function in the first term. That makes it easier to get the quotient rule correct. So when we had a product, we wound up adding. So when we had times here, we wound up having to add two things. When we do the quotient rule, we'll wind up having to subtract. So there's a lot more to the quotient rule. But with it, the way I want you to think about it is you do the derivative of u times v as is, and then you subtract the derivative of v times the u function as is, and then all of that will be divided by the bottom function squared. Okay? And so the reason I want you on your product rule to think about the u prime being in the first factor here is so that you notice that this whole thing looks just like the product rule, except for it has a minus in it. And see, with the quotient rule, you can really get in trouble if you don't do the u prime first, because with subtraction's not commutative. So the order of these two terms right here makes a difference. You've got to have it right, okay? So please try to get in the habit of doing the derivative of the top function first, the derivative of the first function first on the product rule, and make it where the way you're thinking about your product rule and your quotient rule are nicely related so that you can remember them better, okay? All right, now, the chain rule comes into play. You need that when you have a situation where two functions have been composed. Okay? And so when you're doing that, you're going to need to do the derivative of what we could call the outside function. And we'll talk more about this. Chain rule is what 3.4 is all about. Okay? So the chain rule, and I guess the general power rule, I think, is also in 3.4. All right, so what you're going to do is you're going to take the derivative of the outside function, but because this was a u, we also have to do the derivative of it with respect to x. So you do the derivative of the outside function, which is the f, and then you take the derivative of your inside function. Okay? These will make more sense. We're just taking a look at them now before we get started, and then we'll look at these again as we encounter them in each section. Right now, for the general power rule, that is related to the simple power rule, so it starts off feeling like the same thing. You're going to bring down the exponent, then you'll have u, and then it'll be raised to the n minus 1. But you can't stop there, because u, see, we're trying to do the derivative with respect to x, and u is it's not x to the n. It's like right here you've got a 2x plus 1, like a 2x plus 1 to the third, and you're trying to do the derivative with respect to x. So you can't just bring the exponent down and subtract 1. You're going to have to do the derivative of the inside function. So you're going to have to multiply that by the derivative of u with respect to x. Okay? So the chain rule and the general power rule, they're going to come up in 3.4, but that general power rule and the simple power rule, that you really don't need the simple one. The general power one would be good enough, because like if I were thinking about needing to do the derivative of the inside function right here, it's just that that would turn out to be 1, and that's why they didn't need to talk about it. okay, at that point in time. Okay. Now, the derivatives of the trig functions, to prove these, you actually have to use the some of those identities, trig identities for some of them. And then we also need to use, like for sine x and cosine x, if we tried to use the finding the derivative using the limit process, we'd have sine of x plus h minus sine of x over h. And we could prove why we get it to be what we get it to be by using the identity for the sine of the sum of two angles. Okay, but we're not going to really take the time to do that. You just need to know these. Okay, so you need to start memorizing them. And we talked about these in class already. So the derivative of sine is cosine. The derivative of secant is secant x tangent secant x tangent x. And the derivative of tangent is secant squared x. Okay. Now, the way you get the derivative of these, all of these start with cosine, cosecant, cotangent. They're all going to have a negative on them. And the rule for them is going to be related to what the rule was to the function on the left. So sine went to cosine. Cosine's going to go to sine, but it'll be negative. And then secant is like cosecant. Tangent is related to cotangent, but we're going to need a negative on those. And then instead of a secant squared x, over here we'll have a cosecant squared x. You need to work on getting those memorized. Okay. All right, and then there's just, these two should be in 3-2, the sine and the cosine ones. And then these others, they could do them after we know the quotient rule. So that I can't remember if they're in 3-3 or not, but they should be, because once we know the quotient rule, we can justify why these turned out the way they did, because tangent would be sine x over cosine x. So if I knew the quotient rule, I could apply that to figure out what that derivative would turn out to be. Right? And then the derivative of e to the x is in 3-2. And then I believe they wait to do the derivative of the natural log. I don't think they do that until later, like 3-3 or 3-4. But both of these are pretty easy. The derivative of e to the x is e to the x, and the derivative of the natural log of x is 1 over x. Okay?